Hello everyone, my name's Jarrad and welcome to Fixed Wireless 101. This is a series exploring how fixed wireless in terms of the broadband technology works to deliver internet to the customer's premise, and also basically walking you through what you need to know to build your own fixed wireless network. Not that I'm suggesting you do, but everyone likes to have an understanding of things. So in this video, I'm going to focus on antennas, and I'm going to start it off really basic, and then I'm going to take it to the antennas with examples of what you'll see in the real world and when you will use them. There will be a follow-up video, and that one will talk a bit more about antenna patterns and the decisions you make around those. So antennas can be really quite complicated, especially if you've seen all the different antennas you can buy for fixed wireless. You've seen things that don't even look like antennas. A perfect example is a lot of the modern home routers and that. I'll hold one up later on. But I just want to start things out, and this might cause a bit of a stir for those of you who are being brought up with a typical engineering education, but I want to explain it this way because the typical explanation of antennas sort of makes it hard for the non-mathematical scientific guys. So I'll start off with a really simple explanation. There's only one kind of antenna, and that's an antenna which has two sides. Now, some people who know more about antennas will be saying, Jarrad, what do you mean? There's the vertical and the dipole there. There's two types of antennas. Well, there's two practical implementations of a two-sided antenna, but if you think about it, there's really only one kind, and that's the kind where there's something to push against and something to pull against. There's always a pivot point in an antenna, and it's typified by this picture on my screen of a dipole. You can see the red wave, which is the voltage, pivots. The voltage reaches a maximum at the end of the antenna and a minimum at the center of the antenna, and it pivots at that center. So that's one of your kinds of antennas. That's probably the most important antenna that you'll come across, but there is another kind of antenna, and that's called the grounded monopole. And basically all that is someone, well, they figured out in the early days of radio, much by chance more than anything probably, is that you can effectively get rid of one half of the dipole and replace it with a reference to ground. Now, ground is often taken, especially in terms of electrical safety, to mean the earth. And that can be quite literally applied at times as well. But in terms of radio frequency radiation, ground is dependent on the size of the wave. Now, with fixed wireless, we're talking very, very small waves. For instance, the 5.8 gigahertz Wi-Fi we use today is what's called the 6 centimeter band, and that's because in one cycle, now this is only showing you a half a cycle, but in one cycle, think of things as a circle, 360 degrees of rotation, a sine wave. In one cycle, a 6 centimeter band travels 6 centimeters. So that's like the wavefront propagates through space and it moves 6 centimeters before it's gone back and forth. Because when you're talking about RF energy, you're talking about an alternating current. Now, alternating current does the work by pushing and pulling back and forth. It doesn't do it just by pushing. There's pushing and pulling, but the energy is extracted on both sides. That's what you've got to keep in mind. So anyway, back to the point. There's a second type of antenna called the quarter wave ground plane, or the ground plane antenna, in which one side is removed and we're just pushing against this very, very large surface area in relative to the small distance the wave travels in space. So for ham radio operators, making a good ground plane is very, very hard, because sometimes we work on really low frequencies, like say the 80 meter band, and to have an effective ground on 80 meters, that plane that your antenna is pushing against, and bear in mind your antenna's on an 80 meter band, about 20 meters tall, just to be an effective antenna, the vertical monopole is, it needs to push against something that is also at least 80 meters flat, 20 meters flat. So you've got 20 meters up, 20 meters flat. That's a lot of real estate. But it's very, very different when we're talking Wi-Fi in the 6 centimeter band, where having an effective ground could be as small as your hand. Now, I don't want to stick too much on ground. There's a lot of discussion about what makes a good ground and that sort of thing, and that's not the point of this video, because we don't need to know anything about ground really for fixed wireless. So now that we know about that there's two types of antennas, you'll ask, why is that important? And the reason that is because those two different types of antennas make up every other kind of antenna you'll ever see. It doesn't matter how funny looking it is, it's based on either the dipole or the monopole, which has got half the dipole removed. Now, it really does sound like two types of antennas, doesn't it? But the key fact is that it still needs something to push against. You can never ever let that slip from your mind, or you can come up with some wacky ideas that people consider antennas that may sort of work, but they don't work very well. And ham radio is full of all kinds of wacky antennas because it's a hobby that's been around since the days of radio and people were encouraged to experiment. So remember that every antenna you see is made up of either the dipole or the ground plane, which is just the dipole with, instead of having one half, it's had one half removed, and in its place a big surface area that it can effectively push against. So let's look at some antennas. First, I'll just show you two ham radio antennas. They look the same, but this is where a bit of critical, and this is, I guess, a prelude to what you need to do when you're looking at Wi-Fi antennas. They look the same, but they're actually very different. And the thing you look for is this one's a bit thicker in the middle than this one. These are handheld antennas, sorry. They're for little, what people call walkie-talkies, but handheld radios. This one is a ground plane. It has only one half. This one, although it looks like it's only one half, is actually two. It has a wire going up the center and a wire on the outside. That's a coaxial arrangement. So the wire going up the center is connected to this floppy bit, and the outside is connected on the outside, obviously. So what's happening with this antenna, oh, excuse my radio, I'll just turn it down a bit. With this antenna, the energy is going up through here, meeting at the pivot point, and one half is going there, and one half is going here. So it's going up and down like this. That's your dipole. And that's how you can have a dipole on something that looks straight and like a monopole. So anyway, I'll get back to that. Here we have two antennas. They're very large. And they look very similar. Now, they're completely different. This one is a monopole. It's actually a ham radio antenna, and it's used for the 2 meter band and the 70 centimeter band. Now, this one, on the other hand, sorry, is a fixed wireless antenna. It's used for the, what is it? Let me think now. It's used for 2.4 gigahertz or the 23 centimeter band. Now, although they're kind of similar in size, one's about a foot long. No, they're about the same size. One's a foot longer. They're actually completely different. This one is a monopole, and the way you can tell that is because it's got this sort of, hopefully you can see that, yep. It's got this triangular arrangement of wires down the bottom. Or, well, they're not wires, but well, they're a wire in so much that they're a thick thing that current flows in. And that's your other half of the antenna. That's your missing half that the current pushes against when it goes into the antenna. This one, on the other hand, this antenna, is actually made up of heaps of little dipoles. This is what's called a collinear dipole array. In the fixed wireless world, you'll often hear them called omnidirectional antennas. And the reason they call them that is because they use a whole bunch of little dipoles. They only have to be little in the on the 23 centimeter band. They only need to be a half of 23 centimeters. They're not very big. A whole lot of little dipoles, all arranged up the antenna. And what happens is, by having a whole bunch of antennas on a stack, you actually squish the radiation pattern down. Now, normally, I wish I had a ball to demonstrate this. Normally I say, in your ideal physics antenna, when you put energy into antenna, it just goes out around in a big sphere. Now, in a omnidirectional antenna, although they're called omni, and you'd think of them being a big sphere, they are actually directional. And what they've done is, instead of going out in that big sphere, they've squished, much like a pancake, they've squished the ball down into a flat pancake. And what that does is increases the energy going out at the expense of the energy going up and down, which is a good thing when the sky's above you and the ground's below you. So that's your most basic sort of fixed wireless antenna. But I was just using that, well, it's not your most basic. Your most basic are these guys. And these guys are best thought of as a ground plane antenna. There's your antenna, there's your ground plane, whatever's around this. But it's useful to demonstrate that, you know, an antenna isn't what it looks like. Even though it just looks like one big stick, and you can think of it maybe as a vertical, as a ground plane, sorry, it's not. It's a bunch of dipoles all stacked collinearly, and that means in a line, in a stack, basically. So they're sort of, the omnidirectional is your most basic fixed wireless antenna, and as I said, what it does is it squishes the ball down, the ideal ball. Always think of an antenna as an ideal ball. That's the way of understanding where it puts its energy. So it squishes it down so it goes further out. So that's one way. You've just seen one antenna which uses the dipole to build itself. It takes the one dipole which goes into a ball, and it uses a whole bunch of them stacked together within the antenna to increase your radiation by squishing that ball. So there you go. Now, these aren't really, I should go back, I should finish this. These aren't really used that much in fixed wireless. Omnidirectional antennas tend to only really be used in LAN mobile, which is your walkie-talkie service and those sort of things. They're not used very often for wireless or for you know, things like television broadcasting, and that's because they're sort of used for television broadcasting. That's kind of the wrong thing to say, but they're not really used for Wi-Fi very much, and that's because most of the times, especially in fixed wireless, you want to put your energy in a specific location. You're paying a lot of money to be on that tower or whatever, and you want to get the signal where you want to get it. You don't want to, you know, shoot all your signal into the back of a competitor's building or something like that. You want to deliver it to your clients. So in that regard, sorry, these antennas aren't very useful. So we'll get rid of this guy. And that's where you'll typically see something like this. Everyone thinks of these dishes as the prototypical fixed wireless antenna. This is the guy that, you know, beams that signal directly over to your client, right? Well, sort of. This is really complicated antenna. You might think, how is this complicated? It's just a dish, right? But how does it work? Well, for starters, there's two parts of this. Is this the ground plane? No, it's not the ground plane. There's a dipole in here. And there's something else in there too. It gets even more complicated. But let's take it apart for a second. This is a reflector. All this does, and it's parabolic in nature, all this does is take the energy coming out of that center part I removed, is take the incoming waves and focus it on that center, the center point that I removed, and vice versa. It's a reflector. It's basically a way of helping the energy reach your antenna. So we take a look at this guy. That's our antenna. It's our radio as well, actually. Fixed Wi-Fi is really cool because the radio is built into the antenna nowadays. There's no feed line or coaxial cable to lose energy in. Very efficient. So this looks like, well, this is the antenna, but it's even more complicated than that. What's in here? Well, that goes back to this guy. This is a horn antenna. Now, Why do you call it a horn antenna? It's because it uses a specially designed, in terms of maths, horn to couple, which is a way of saying connect the energy from the antenna to the outside world. So the horn part does the coupling. Now, the horn part may look a bit similar to this, and that's because that's essentially a bit of a horn as well. It certainly is in the bigger antennas. I don't know if it is in this sort of small antenna. And by bigger, I mean, you know, like James Bond GoldenEye Arecibo antenna. I don't mean bigger fixed wireless one, although some may use horns. This is essentially that part. So we'll take that off and have a look what's in here. Now, I'll hold it up to the video. Is that right? Yeah. Can you see it? No, sorry, I got a bit of shadow of the camera there. And inside, hopefully you can see that there's two little prongs there. What those little prongs are, they're the actual antenna, and they're built right into the radio itself, which is so cool. From a ham radio operator's perspective, that is really cool. Basically because there's no loss. And what they do, what type of antennas are they, you're wondering? How do they work? Well, they're not dipoles. And the way you can tell they're not dipoles is because there's no pivot point in the center. They're ground plane antennas, or specifically probably quarter wave ground plane antennas. Why do I say quarter wave? It's because in terms of ground plane antennas, it's very efficient to work with a quarter wave long ground plane antenna. And in terms of dipoles, it's very efficient to work in a half wave long antenna. That's why I use those words. But inside this radio, you've essentially got two little dipoles with half of the antenna cut off, and that other half of the antenna has been replaced with a ground, which is the housing of the radio. And then you go, why do you have two? Well, fixed Wi-Fi is really cool. Because the wavelength is so small, you can actually polarize your waves. One can be vertically polarized and one can be horizontally polarized. You can do that in all kinds of radio, but in ham radio with the bigger waves, they tend to all sort of mishmash together and it doesn't really make much of a difference. But in fixed wireless, it makes quite a bit of difference. And certainly the performance of your link between your transmitter site and your receiver site depends on the quality of your, well, it depends on the quality. Your link quality depends on how well your vertical and horizontal polarization is maintained. But anyway, I digress. Basically, what you've got here is two little quarter wave verticals, and what they do is they push against the housing of the radio to excite energy in this cavity. Now that cavity, if we weren't to put anything on it, wouldn't connect very well to the air. So the radiation wouldn't, not only would it be very hard to push radiation out of this, it wouldn't actually go anywhere useful. It would probably go randomly anywhere. That's basically why you can't turn a microwave oven into some sci-fi super weapon that people have made videos of, but they've actually just used Photoshop, right? And so what they figured out is they needed some sort of way of making it so that when you go from essentially a small space to a very big space, the waves can, you know, live their happy little lives and not get too anxious, or something similar to that you can explain with numbers, but not very well with words. So you get the horn. And you figure out how to put it back on, and you squeeze your horn on, and all of a sudden the waves that you're generating with your two quarter wave ground planes, you don't need two, but there are two in this, it's more efficient to use two. Basically lets you have 2 times the amount of bandwidth, or what I'm trying to talk about is the amount of data delivered. You have twice as much if you have a vertical and a horizontal, so that's why there's 2. So, I lost my half wave dipole. Oh well. So your horn, it's happily coupling it to the environment, but you can have many different types of horns. Now, depending on the shape of the horn, it can either be a really tight beam, and this is much like a flashlight. You know, you got the old mag light where you twist the end and you can adjust it from wide to really, really sharp. That's what a horn is, except you can't twist the horn, except to put it on and off. But anyway, that's just this design. So this one's a 45 degree. It's really simple. Just like a flashlight, it shoots out the beam at 45 degrees. So if you think back to our ball, our typical antenna, the ball, what that's done is it said, I'm going to squish that ball so it can, on all from the middle, if you think of the middle ball, I'm going to squish it in all directions except for a wedge, a 3D wedge, that's a quarter, that's 45 degrees in angle. Yeah, it's really hard to put maths things in words without a whiteboard. What can I say? So that's what that does. Now, going back to our dish, all the dish does, and your bigger dishes, you know, you've probably seen them with your Foxtel and stuff like that as well, is they've got their 2/4 wave ground planes. They've got their horn to make it easier to, you know, get out into big bad world. And they've got that shooting at the dish, and the dish is just a big reflector. So when you see an antenna like this, or an antenna like this, sorry, I always encourage you to have a little bit of a think about how it's made up. Because, as I said, all antennas go back to 2 basic designs, and all of them go back to 1 basic principle, and that's of a push and a pull. And if you think about that picture behind me, which is just on Wikipedia, or if you think about alternating current, you know, up and down, the waves in the sea, that sort of thing. If you think about that, it makes a lot of sense as to why there has to be something to push against and pull against, the pivot point. And yeah, every antenna is made up of that basically. So yeah, in all situations, you are just talking about, depending on how you design it, whether it's using a horn, a reflector, a combination thereof, or a collinear array. Actually, I'll show you that. There's all your little dipoles. Hope you can see that, yep. So in all applications in fixed Wi-Fi, irrespective of what it looks like, the whole point is to use the 2 basic building blocks, or the 1 principle, to get your signal where you want it to go. And do some have advantages and disadvantages? Yes, they do. And I want to cover that in a separate video on antennas, because it's a complicated subject and we've already taken 20 minutes. And I'll talk about, but you know, basically, yeah, it really does just boil down to using 2 principles to push your signal in the direction you want it to go. That's all you have to think about with antennas. I encourage you to look at antennas and go, how does that work? Where is the dipole? Where is the monopole, or the quarter wave ground plane? It can be a fun activity if you're a nerd. And in the follow-up video, I'll talk about why some of these different types exist and what their advantages and disadvantages are and why they're used. So hopefully I have somewhat uneloquently, is that a word? I don't know. Hopefully I've badly explained how antennas work. And I say badly because it's more or less impossible to explain antennas without mathematics. It's just not something the English language was really well suited at doing. We have to use a lot of analogies, a lot of metaphors, all that sort of stuff. That's the beauty of maths. If you can understand it, you just read the numbers and you know how the antenna works, right? But if you're watching my video, you're probably the normal kind of person, you know, the 95 or whatever other percentage of people are, that never really got past, you know, adding up your tax bill, doing a spreadsheet for your groceries, I don't know, whatever you do with numbers, right? Counting 1, 2, that sort of thing, waiting for your birthday. You're probably one of those people, and that's why you're watching my video. So hopefully I've badly explained in English how an antenna works, and you do actually understand, even though I badly explained. Anyway, that was long-winded. I hope you enjoyed it. Let me know in the comments what you thought, and I look forward to making my next fixed wireless video, which will cover when you use different antennas. So basically, when you decide to squish the ball, how you decide to squish it, and when and why you decide to squish the ball. I think that's how I'd say it. So that's video number 2. Probably won't be quite as long, not as difficult a concept to put in the English language. Cheers, or 73 for ham radio viewers. This is Jarrad, and my call sign is VK3BL.